Now we have finished our understandings of CDCLT, and we will start in the phase of understanding various theories and how to develop decision procedures for those theories. First, we will study linear rational arithmetic and followed by linear integer arithmetic. Before understanding how to implement linear rational arithmetic theory solver, we will first understand few linear algebra basics to see what kind of proof system we need to reason about linear constraints. So you must have seen in your high school this kind of proof rules where you have two linear inequalities and you take the linear combination and then you obtain this particular inequality. So what you can do, you multiply by 1 here, you multiply by half here, and you sum them up, then you will find this linear inequality. In fact, you will get x plus y less than or equal to 4. But this implies this, therefore you can conclude this inequality. The important fact is that this is very intuitively to observe that this is a correct reasoning. However, we do not know immediately, obviously, this is a complete reasoning. How do we know that this way of deriving linear combinations is the only way to derive new facts from a given set of facts? And in this lecture, we will prove this theorem. So what is the theorem? Then if you, let's suppose you have a matrix A and a vector B, and you have these constraints Ax less than or equal to B, and C be a row vector and delta be a number, and a typical implication between bunch of linear inequality and implies another inequality can be written in the following form. Now the question is, this implication holds or not? So if you want to show that if implication holds or not, you have to simply show that there exists a delta prime such that Cx less than or equal to delta prime is a linear inequality which can be written as a non-negative linear combination of the inequalities in EB, Ax less than or equal to B. This theorem is also known as a Farkas lemma. For example, in our case, we saw an earlier slide where we took the linear combination and we found that this holds. Now we will embark upon proving the completeness of this reasoning step. In this lecture, we will be using a lot of facts about linear algebra. For example, linear independence, rank of set of vectors, vectors versus row vectors, hyperplanes, affine hull, etc., etc. So please, if you're not familiar with linear algebra, go back and freshen up your linear algebra before embarking upon this course, this lecture. Okay, so let us define a concept of cone. A cone is a set of vectors is a cone if any positive linear combination of two vectors, okay, is within the cone. For example, let's suppose you have two vectors and anything in between, you can put that in the cone, and this we'll call it cone. A cone is called finitely generated if there is exactly m vectors, a finite set of vectors, such that their positive non-negative linear combination gives you all the vectors inside the cone. And finitely generated. Here's an example where you can see that the cone C is defined by two vectors x1 and x2, and then you just take the non-negative linear combinations and you obtain this cone, which can be written in the following form or this form. Here are two vectors and their linear non-negative linear combination is here. However, a cone definition is far more general. It does not mean that every cone is finitely generated. You can imagine a cone should be like this, and this is also a cone, but it's not a finitely generated cone.